by 12, right? So 1500. So it's equal to 18,000 pound-inch. Okay. So what we need to identify from here, right? What we need to identify from here is we have stresses in two directions. We have a normal axial load, a torque, and a moment. Okay. So we know that stress X, right? So we're going to write up the formula. Stress X, normal stress X, is equal to Px divided by A, right? And it's going to be compression. And you guys also know this is going to be plus or minus, right? Depending on where the element. So after this, I'm going to draw the element. So you guys will get really, really excited. I mean, I hope so. Okay. So this is equal to mz divided by izz multiplied by y. Okay. And then the shear, right? So we also know the shear. The shear, there are two, right? The shear, we can look at TR, because there's a torque, TR over J, plus, and someone, oh, not again, okay? So this is VQ over IT. Okay, so that is our shear, and now all this should be really, really familiar for you guys. Okay, so now we are going to apply. In fact, once we have done this, right, we divide. We have over here. We have already applied the Tresca. Okay, Tresca criteria. Okay, we in fact have applied Tresca criteria already. Okay, so now we're going to analyze the shaft now. Okay, we're going to analyze the shaft. So this is where, yes.
With the translation you drew, shouldn't that be PZ and TZ and MX?
Based on this transformation, right?
Wait, am I reading it? Oh, I read the X's and Z backwards.
Okay. Oh, my bad. My Z is not right. Okay. So now I'm going to take this shaft and we're going to draw 4 elements. Okay, I'm going to draw. Some of you say, why 4 elements? Okay, so I'm going to construct 4 elements. Okay, so I'm going to construct. I wonder because my screen is so dark, I don't know how clear is this. Hold on. Okay. So I'm going to draw one element here. One element here. One element at the below. One element at this side. Okay. So I'm going to call this my element A. Element B. Okay. So now I'm going. So this is my transformation. X, Y, and Z. And you guys are going to love this. Okay. Right. So if you look at element A, okay, so this is my X. That's my element A. X, Y, and Z. Okay. So if we were to look in terms of planes, right? So this will be my X, Y plane, right? This will be my this will be on my Y, Z plane. And this one will be my X, Z plane. Can someone tell me which one is in plane?
XZ.
Yeah, so this is my in plane. And these are my out of plane. And these are my what? Out of plane. Okay, I'm going to draw element B now. You know, it's so nice. You know, I'm so happy. It's like full circle. Once I start doing this, and you guys find it easy, it means something has gone wrong with you inside. You know, it's a good thing that has gone wrong in you, not a bad thing. Okay, it's like you see the light. You know, initially when I drew this, like you guys are, oh holy shit, we're all going to die. Some of you see, we died. This is not a, but anyway, okay. So yeah, this is not a very good drawing. I do 100% apologize. It is crabby. Yeah, this is better now. So you say, Eugene, no bloody difference. Okay, so we know down here the most important plane. So this is my YZ plane again, right? And this one is my XY plane. And then we have another plane, which is this surface over here, right? Right. Okay. And then this one over here is so-called my see, I'm freaking lost already. This is my okay, don't worry about that plane. I'm lost already. What I want to highlight is this, okay?
That's the XZ.
XZ, right? So this is my XZ plane. Okay. So now you know that this is your what? This is your in plane, and this is your what? Out plane, and this is your out of plane. Does that make sense now? Yes or no? Okay, so it depends on the structure, okay, that you're looking at, right? Remember, in one or is in your exam. No, it's not your exam. One of the example over here, right? One of the example. Let me see. Could I remember? Over here. I want to show you all this. So if you look at the yield, there's a lot of yield in what? In tension, yes or no? The yield in shear, you don't have a lot of values, right? You don't have a lot of values. That's why if now you're given this, okay, maximum tensile is 690, you don't know what is the what? What is the shear? So that's where when you apply Tresca, right, you declare that is equal to 690 divided by 2, which is 345. Does it make sense? Right? Okay, now let me see, like this example over here. There you go. Okay, so we have drawn. Oh, if it's like, I don't want to show an example where you have a circle. I want to show you an example then when it's not a circle, like when it's a not here 10, or maybe is it week 9. Okay. Okay, let's look over here, right? There is your element H, yes or no, right? So when you look at element H, you construct your element now. Okay, so if this is your transformation, this is your Y, this is your Z, okay, and this is your X, right? So for this case, your XZ plane is the one that is in what? In plane. And then the other two, so over here, this is your YZ plane, right? And this is your out of plane. And then for this case, your XZ plane is also your what? Out of plane. Okay, now we can see all this now. Okay, so now you know what is in or when is it in plane, out of plane. Am I right or am I wrong? Are you okay? So I have no, oh, someone wrote something, or maybe it's long time ago. I do apologize. For a finite element, you can draw any surface as bigger. Isn't it subjective? Hey. Mira, what do you mean by subjective? So the
sorry, I just mean that when you're drawing your elements, you're choosing to draw one plane as bigger, and then you're picking that plane as in plane.
Yes.
But really, you could draw like a cube, and then say that that's element. Isn't it subjective?
No, the in depth is never a cube. You can see over here the in depth is never a cube, right? The in depth means towards the y direction in depth. So the surface where you're interested, there is always a square. The in depth is always a thin layer.
So the surface of the element is always in plane then?
Yes. Okay,
Okay.
like for this case. Okay, like for this case. Okay, like where are we now? Gee, I'm super lost now. Right? So all this, right? You look at the surface I've drawn, is always the surface that is what? In plane, right? But not necessarily the in plane will have the maximum shearing stress. Does that make sense? Right? It all depends on the loading condition. Okay. Okay, I think I'm ahead of myself. Okay, right. So now we know all the elements now. Okay. So the next thing we're going to do, are we okay? Can I move on or no? Okay, I got no reply. Means I'm given blessing to move on. So now, we have to now identify where the maximum stress is, right? So I'm going to draw a circle. Yeah, I'm going to draw a circle now. Is this a circle or does not look like circle? It does not look like a circle because it's not a circle, right? So now, so draw our transformation first, x, y, z. So where I'm looking now, well, or where we are looking now, this is, okay, this is a transformation. So this is my y, and this is my z, right? So the first thing we have to, so we know that this is element A, right? Over here, element B, right? Over here, element C. Then over here is element D, right? So which element has the highest stress based on the loading condition? So you have to analyze again. Okay, I repeat, you have to analyze again. Okay, which element has the highest stress? Okay, so now we are going to look at element. We're going to formulate a table. Okay, we formulate a table. So element A, element B, element C, okay, element D, right? So we have a vertical line. Okay, so the first thing we're going to look at the shear stress, right? So the shear stress formula is, we know that is equal to TR over J, right? That's a shear stress. So if we look at element A, B, C, and D, the radius, right, based on that formula in terms of torsion, the radius is all the same. Yes. So all of them will see the same level or same magnitude of shear stress. So shear stress, no change. So this is TR over J, TR over J, TR over J, TR over J. Okay, that's TR over J. Now, I know some students, okay, probably Mariam will say, Eugene, I want to put in a shear force. Then Mariam will say, Eugene, I want you to include this. Tau is equal to BQ over IT. Yes or no? Right? So what if now we have an extra V coming down? Okay. So that's where now you guys see there is easy peasy, right or not? Right? If you have a shear stress coming, a shear force coming down here, B, right? So if I were to sketch the distribution, right? If I were to sketch the distribution now, right? And this is it's not a thin one analysis, it's a thick one analysis, right? So now this is my shear, right? And this is my my y direction, right? So we know that the distribution will go like this. Yes or no? So if this is element A, element B, element C, and element D, right? What will happen? Anyone? So element